First of all, thank you very much first of all for choosing me, and it's a great honor to be chosen for this prize. And thank you very much for the introduction. It was a little bit embarrassing for me, but okay. I'm very happy to be here, and I would like to talk about some results obtained in the last year in collaboration with many people, including Giulia Basti, Chiara Boccato, Cristian Brennecke, Cristina Caraci, Serena Cenatiempo, Alessandro Giati, Giulio Pasqualetti, Diane Saint-Aubin, and Severin Schraven. So Giulia and Serena, I'm very happy they are here. And these are a series of results concerning system of many-body particle, quantum system of many-body particle exhibiting Bose-Einstein condensation, for which we develop a mathematically rigorous version of Bogoliubov theory in order to say something about their behavior, the stationary behavior, the equilibrium behavior, and also the non-equilibrium behavior. So let me start the talk. So, as I was saying, we would like to describe a system exhibiting Bose-Einstein condensation. Bose-Einstein condensation is a phenomenon which was first predicted by Bose and Einstein already at the very beginning of quantum mechanics, so in the 1920s. And it means, or it refers to this fact that if you look at a certain system of particles in quantum mechanics and you look at very low temperature, then you can see that all the particles behave in the same way, so as if they were described by the same one-particle wave function. That's what condensation means. And as I was saying, it was first predicted in the 20s, more than around 100 years ago, and it was only seen experimentally. It was only discovered experimentally much later. So in 1955, there were the first experiments exhibiting Bose-Einstein condensation. This is a typical picture from these experiments in the 90s. So you see what happens when you lower the temperature. So this is a picture of a momentum distribution of the particles of a system of many particles, maybe around 1,000 particles or something like that, depending on the temperature. So this is a bit higher temperature, and when you decrease the temperature, and you see that if the temperature is low enough, then there is a peak. So there is this a high probability of finding particles with momentum 0. So that's what condensation means. It means that a macroscopic part of a particle, so if you have n particle, a number of particles which is proportional to n, they can all be described by the zero momentum one particle wave function. So in this case, just a constant. Okay, good. And from the point of a mathematician or a mathematical physicist, given these pictures here, for example, it is of course interesting to try to understand the behavior of this system starting from a microscopic description of the system you're looking at. So you want to look at the system, you think of the system as consisting of its elementary component, which can be atoms, for example, and you want to describe the fundamental interaction among these particles, and to understand, based on this fundamental microscopic point of view, you want to understand the emergence of this kind of picture and other properties of these systems. Okay, so let me start my talk by briefly reviewing some of the main postulates of many-body quantum mechanics, namely the postulates that then are going to be useful in order to understand what I want to say during the talk. So at the macroscopic level, you can describe a system of n particles in quantum mechanics through a wave function. A wave function is a square integrable function, complex valued, on space. In this case, I took R to the 3n. So each particle lives in the three-dimensional world. We have n particles. So in total, we have 3n degrees of freedom. And the wave function is a function of the position of the n particle. And the interpretation from the point of view of physics is that if you take the absolute value squared of this function, of this psi n, then you get the probability density for finding particle 1 close to x1, particle 2 close to x2, and so on. Okay, so in particular, this means the wave function is always normalized so that the L2 norm is equal to 1. Good. Now, if you know the wave function of a system, you cannot just describe the distribution of a position of a particle. You can predict the outcome of experiments measuring any observable, any physical quantity of your system. Okay? So observables here are associated with self-adjoint operator acting on V space, and the expected value of an observable, say, associated with the operator A is the L2 product between psi n, A psi n. Okay, so that's how you can use the wave function to make any prediction about your system. Good. Now, if you look system of many particles, some care is also important concerning the symmetry, the statistics of the wave function, so the behavior with respect to permutation of the particles. Now, in physics, in nature, there are two types of particles, which are known as bosons and fermions, and they behave different, the wave function behaves differently in the two cases. So here, since we want to describe Bose-Einstein condensate, we are going to focus on system of bosons, which means we are always going to assume that the wave function is symmetric or is invariant with respect to any permutation of the m particle. Right? If you switch any two of these coordinates, the value of the function does not change. Okay? If you look at system of fermions instead, you have to multiply here with the sign of the permutation, but then you cannot have condensation. You cannot have many particles in the same state. So if you want to look at the Bose-Einstein condensate, then you better look at system of bosons. Okay? Good. Now, a very important observable is the Hamilton operator. And the Hamilton operator is the operator, the self-adjoint operator, which is associated with the energy of the system. And typically, at least in this talk, the Hamilton operator has the following form. Hn, I call it, is a Hamilton operator for m-particle system. It consists of two parts. The first part is a sum of n terms, and each one of these terms only depends on one variable. Okay? So the first part here describes non-interacting system. It's an energy which you just get by summing the energy of particle 1, particle 2, particle 3, and so on. The second part, the sum over all pairs of particles, describes the interaction between the different particles. In this case, every term in this sum depends on two particles, xi and xj. You can also ask what happens if you take terms which depend on more particles. That is also an interesting question, but that's not something that we're going to do in this talk, at least. Good. Okay, so Hn is defined as a self-adjoint operator acting on this Hilbert space. So this S here reminds us that we are only looking at wave functions that are symmetric with respect to permutations. So why is the Hamilton operator important? Well, it is important because it generates the time evolution of the system. The time evolution in quantum mechanics is described by the Schrödinger equation, which I wrote down here, which tells us that if you call psi n of t the wave function at time t, the derivative with respect to t times I, this is a complex number I, is given by the action of the Hamilton operator on psi n of t, which means that you can get the time evolution just by applying the unitary group generated by Hn on the initial data. That's why the Hamilton operator is so important. That's why if you understand the properties of Hn, you understand also the dynamics. If you understand the spectral properties of this operator, what are the eigenvalue, what are the eigenvector, how does the spectrum is, continuous, the discrete, and so on, this tells you all you want to know about the time evolution of the system. Okay? For example, this means that the stationary states of this problem are just the eigenvector of the Hamilton operator, because if you start at time 0 with an eigenvector of Hn, this guy here is just a simple phase which plays no role when you compute expectation. Expectations are always quadratic. Good. Okay. So let's be a little bit more precise. Let's now switch to this system exhibiting Bose-Einstein condensation that we want to describe. You remember the picture in the first slide. So if you want to describe dilute quantum gases in the experiment that then give rise to this Bose-Einstein condensate, it is good to look at particles in the so-called Gross-Pitayevsky regime. So let me try to explain what this means. So if you are in the Gross-Pitayevsky regime, when you look in the system of n bosons, at the end, n is going to go to infinity, right? We want to think of n as being a large parameter. We will be interested in asymptotic expansions in the limit as n goes to infinity. So we want to look at n bosons, which are moving in some domain with volume of order 1. And for simplicity here, we just take the translation invariant setting. So we take the n particles moving in the box with volume 1 and with periodic boundary condition, or if you prefer, the unit torus. And then we let these particles interact with an interaction whose effective range is very small, of the order 1 over n. Okay? So that's what characterizes this Gross-Pitayevsky regime. So if you want to a picture, so this is my box with size of order 1, and then you see every particle has some potential, interacts with particles which are at distances of the order 1 over n. Okay, so we are in 3 dimensions, so the typical distance between these particles is 1 over n to the 1/3. It's much larger than the effective range of the potential. This means that this regime describes a very dilute system. Collisions are very rare, because you need particles to be very close in order to see each other. Good, so this is the physics, so let's come to the mathematics. If you want to describe the situation, then the Hamilton operator you should take has the following form, Hn. So the first part is the kinetic energy of a particle. Again, this is the non-interacting part of the system, of the Hamilton operator. It describes free-moving particles, free-moving bosons. And then there is the interaction. And the interaction scales with the number of particles, and it has to scale so that the effective range of this guy is of the order 1 over n, right? Now take v is a function. Suppose that it is positive, non-negative, so it means the interaction is repulsive, okay? And suppose that it has a short range, so compact support. If you make this assumption, it is clear that this term vanishes unless xi minus xj is of the order 1 over n. So this corresponds to this idea that you want particles only to interact when they are at distances of the order 1 over n. Okay, so that explains why there is an n in the argument of v. The n square in front is because otherwise, if you have this short interaction, this very short range potential, if you don't rescale also the amplitude of the potential, you will not see anything. Okay? And in fact, the choice with this scaling here is exactly so that the scattering length, which is a physical quantity which describes the effective range of a potential, is of the order m-1. So let me briefly recall, since it will play an important role in the rest of the talk, let me recall the definition of scattering length of the potential V. Good. So the scattering length is defined through the solution of this equation here. This is an equation on R3. It's a one-particle equation where we take the potential and we take the Laplacian, and we look for solutions of this equation with the boundary condition. We want that f goes to 1 at infinity. Okay? And then, of course, I told you we want to assume the potential to have compact support. So if you are outside the support of the potential, this is 0. So you're looking for solution of Laplace f equal to 0. And we know how solution of the Laplace f equal to 0 equation look like. In particular, if you want this boundary condition here, the solution should look, when you are outside the range of V, it should look like 1 minus a certain constant divided by x in 3 dimensions. Okay? And the constant here is what is called the scattering length of a problem. Okay? So the scattering length determines how fast, so this is a picture of a solution. It should be 1 at infinity, and then it bends down, right? It bends down because the potential is positive. Particles do not like to sit close to each other. They kind of repel each other. But how strongly it bends down is determined by this parameter A, by the scattering length. Here. An equivalent characterization of the scattering length is given by this integral here. If you take the solution of this equation and you integrate against the potential V, you get exactly 8 pi A. It's very easy to check that the two definitions are equivalent. Now, if you take this definition and you ask, okay, what happens now if you rescale the potential? Instead of V, I take now n square V of nx. Okay? And then you see immediately that once you know the solution of this equation, you also know the solution of this equation. A simple rescaling, right? Because if you take the Laplacian of f of nx, two factors of n are going to jump out, and we're going to cancel this n squared here. So up to rescaling, this is the same equation as this one. And this tells you why multiplying with n squared was the right choice in the Hamiltonian in the first page. Good. Okay, so that's, you see immediately when, by this scaling argument, that the scattering length of this rescaled potential is exactly the scattering length of V divided by N. Good. Okay, so now you know what is this scattering length, so I can start to describe mathematical property of the Hamilton operator. So let me go back. So now I'm going to describe spectral property of this operator Hn, which acts as self-adjoint operator on this Hilbert space. So now the Hilbert space, we stick to this box lambda instead of R3, but otherwise it's the same operator as we had before. Okay. So the first result, or rigorous mathematical result about the spectrum of this operator were obtained by Lieb, Ingvason, and Robert Salinger. So they go back to around the year 2000. So the first result is by Lieb and Ingvason, and they were able to estimate the ground state energy of the Hamilton operator. This is the lowest eigenvalue. Okay, so the Laplacian is positive, the potential is positive, so this is a non-negative operator. We are on this finite volume, so the spectrum is discrete. Let's look at the first eigenvalue, and what they prove is that the so-called ground state energy, as n in the limit of large n, is given by 4 pi times scattering length times n plus lower order term, which go to 0 if you divide by n. Okay, so you see the first thing that you can observe is that, well, to leading order at least, the ground state energy only depends on the interaction potential through the scattering length A. It is not important what is the precise profile of the potential. The only parameter that you see appearing here is A. Okay? So that's already something interesting. And then, well, the energy is proportional to n, so it's proportional to the number of particles in the system, and then there are lower order correction. Good. A couple of years later, Lieb and Salinger were also able to prove that the corresponding ground state vector, so the eigenvector associated with this ground state energy, exhibit condensation in the sense that I explained in the first slide. So let me try to give a little bit a more mathematical definition of what condensation means and what they proved. So they proved that if you take any wave function, right, whose energy is to leading order comparable with the ground state energy. Okay, this is the ground state energy. In particular, if you take psi n to be the eigenvector associated to En, this is true by this result here. If this is the case, then the one particle reduced density associated with psi n satisfies this equation here, where phi 0 is the zero momentum one particle zero momentum wave function, so it's just the constant in this box lambda. So let me try to explain what this means. So what is this one particle reduced density, gamma n? Well, this in the language of probability, this is the one particle marginal. So you have something which depends on n particles. You are only interested on observable depending on one particle. So you integrate out n minus one particle and you see what happens. Okay? Of course, in quantum mechanics, probability is quadratic in the wave function. So instead of just taking the marginal like you do in probability theory, here you have to take two copies of the psi and you take what is called the partial trace. So you integrate out all the degrees of freedom of the last n minus one particle, you end with something which is acting on the one particle space. Okay, and this gamma n, it is normalized so that the trace is equal to 1, and the fact that the expectation in the state phi 0 goes to 1, the meaning of this limit here is that as n goes to infinity, the ratio of particles, we have n particles, right? So we have many particles, but the ratio of particles which can be described by phi 0, which are in the state phi 0, the zero momentum state, in the picture in the first slide, particles which are at the peak, right, goes to 1. Okay? So in this sense, you can conclude that almost all particles up to a fraction which goes to 0 as n goes to infinity, can be described by this one particle state phi 0. Okay, let me stress the fact condensation in this sense, in the sense of the reduced density, does not mean that the corresponding many particle wave function, so if you take psi n to be the ground state, can be thought of or can be approximated in any sense by the product of n copies of phi 0. Okay? Let me try to convince you that this is a weaker statement that we have here. Well, if you take psi n to be just the product, and you compute the energy, it's very simple computation because phi 0 is 1, so phi 0 to the power n is still the function, the constant function equal to 1. So the expectation of the Laplace operator is 0, you don't see it. You only see the expectation of a potential, and if you do the computation, you get something like that. But this is much larger than this 4 pi a times n, because the Fourier transform of the potential at 0 is the integral of v of x. A instead, or 8 pi a, was the integral of v of x times f, which is smaller than 1. So it means this number here, v hat of 0, is always smaller than 4 pi times n. And then you multiply a smaller number by n. Okay, so the difference between the true ground state energy, which we know to be the right-hand side here, and what you get with this trial state here is of order n is huge as n goes to infinity. Okay? So in this sense, while you have condensation, it is not a good idea to think of a ground state like that. The point is that what makes the energy go down from this to this are correlation among the particles. Correlation that you don't see anymore if you integrate out all the particles, and therefore here you still get 1, but the correlation are what are responsible for lowering the energy from here to here. And this will be a recurrent theme in this talk, correlations and their role to determine the energy. Okay, so these are sort of old results, and now I can start with some more recent results, which are an improvement or an attempt to improve this result of Liebs, Haringer, and Ingersoll, if you want. So the first result goes back to already 7 years ago. So it was obtained with Chiara Boccado, Christian Benneker, and Serena Cenatiempo. And it states the following. So here we assume the potential to be in the space L3. Okay. Then what we prove that the ground state En, remember that they showed that in the limit is given by 4 pi a times n plus lower order. And here we show that the lower order is at most order 1. Okay. And not only we prove that, we also give a better estimate on condensation rate, right? So like before, we take a wave function in the Hilbert space, normalized. We assume that the energy of a wave function is comparable to leading order with the energy of a ground state. And then we show not only that this expectation converges to 1, but that it converges to 1 with rate 1 over n. Okay, so the difference to 1 is only proportional to 1 over n, so it's very small. Right, so what does it mean? Well, it means that the ratio of particles which are not described by phi 0, so 1 minus the ratio of particles which is by phi 0, is of the order 1 over n. So if you have n particles, most of them are still described by phi 0, and it is only a bounded number of particles which is orthogonal to phi 0 in a certain sense. Okay, so that's an improvement on the bounds for the condensation. Very good. Now, if you look at this, well, the next natural question is, well, what can you say about this constant C? What is the next order is order 1, but can you determine it? And of course, determine the order 1 contribution to the ground state energy is not only an improvement on the estimate for the ground state energy. If you can resolve the energy to better order than order 1, then you can also start to see the excitation. And this is important for physics. You don't only see the ground state, but you also see the next eigenvalues in the spectrum. So that's what came a little bit later. So this is the expansion for the ground state energy to second order, right? So you recognize again this factor 4 pi a times n, that was already there before, but now you also see contribution like this one here, this factor here, and this strangely looking sum here, which are of order 1. So this is the next correction to the ground state energy, and then the lower order terms are smaller. They go to 0 as n goes to infinity. Okay? So this factor E lambda times a square is a bit artificial. It is there because the scattering length, we define the scattering length 0 through an equation on R3. But now our particles are confined in this box, in this torus, right? So which is, the volume is smaller. And of course, the scattering takes place on the scale 1 over n. So more or less they are the same, R3 or this box, but not quite. If you want to get the energy to this precision, then you also get correction to order 1, which are due to this, if you want, wrong definition of the scattering length. If you define the scattering length on the box, directly on the box, then this term here would disappear. So what is more maybe characteristic of this formula is this sum here. This sum here is very typical of Bogoliubov theory, which is the method that we developed in order to derive this result, and maybe later I will have time to say something about it. Good. Maybe you are surprised, I mean, this is a sum over the lattice Z3. You are surprised that the sum converges, I mean, because this looks like something which diverges, but in fact, if you expand this square root here, you will see that the term p square and the constant term and also this guy here are going to cancel, and the parenthesis is actually behaving for large p as 1 over p to the 4, and therefore it's summable. Just a small remark. Okay, so if you can resolve the energy to order 1, as I was telling you before, then you should not be surprised that we can also say something about the excited eigenvalue, the spectrum above the ground state, right? We want to stay close enough to the ground state, so we look at the spectrum of the difference here below a threshold psi, or zeta, more precise. And what we prove is that the spectrum consists of eigenvalues which have the following form up to errors which go to 0 as n goes to infinity. Now, let's try to look at the form. So what is important here, we are summing over all momenta, right? But NP is only allowed to be an integer number. Okay, so how do you determine the spectrum? Well, for every p, you have to tell me how many excitations you want with momentum p, that's the number np. Each excitation with momentum p costs this energy here, so if you sum over all p, you get the total energy of this collective excitation, okay? So this is a quasi-particle interpretation. This allows a quasi-particle interpretation of the excitation of this Bose-gas, of this Bose-Einstein condensate. Good. So the square root that you see here is known as the dispersion law of the excitation. How much energy you need to create an excitation with momentum p. And once you know that, you can determine the whole spectrum. Good. Okay. I wrote something here. Of course, from a point of view of physics, knowing the excitations gives you much more information than knowing only what is the ground state energy, because the excitation is where the physics takes place. In particular, an important observation about this dispersion is that for small momenta, close to 0, this grows linearly in p, not quadratic as for free particles. And this is the reason, I mean, this has been used to show that these systems exhibit superfluidity. So this was this argument going back to Landau. This is the Landau criterion for superfluidity. Okay. And I should say, I mean, I've been talking here about result related to this Gross-Pitayevsky Hamilton operator. There were results before ours which addressed the same question for different model for mean field type models where the interaction, well, particles were still in the box, but the interaction was not local, so everybody was interacting with everybody else, essentially. That's the difference. Okay, so let me discuss some more recent results. So once you get the formula for the ground state energy to order 1, then of course you can still ask, okay, well, what is the next order, right? And the next order turns out, well, the first order is n, the second order is order 1, maybe the next order is 1 over n, but maybe not quite, because turns out there is a logarithmic correction. So the next order, the third order correction, is of the order log n divided by n. And that's what we recently proved in a paper with Cristina Caracci, Alessandro Olgiati, and Diane Saint-Aubin. Okay, so what is maybe remarkable in this formula is the fact that it still only depends on the scattering length. You see, up to third order, the energy only depends on the potential, on the interaction potential through the scattering length A. It does not matter what is the precise form of the potential. The only thing which is important for the energy is the scattering length. And now, of course, you can ask, okay, what is the next term? Well, the next term is expected to be 1 over n, but it's not going to be universal anymore. It's not only going to depend on the scattering length. It depends on other properties of the potential. Okay? So in a certain sense, going up to here, this is what is the most general possible universal result, which only depends on the scattering length. Okay, good. Let me also, well, present some other extensions of the result that I presented. So I didn't mention it, but maybe you noticed, in the assumption of all this theorem, we always assume the potential to be, I think, in L3. Now, the method that we developed to prove those theorems, you can probably extend them a little bit, and you can maybe prove the results for all integrable potential, but you cannot go beyond what is integrable. Okay, so you will always need L1 for a method that I discussed, that we used to prove the previous result. But from the point of view of physics, it's also interesting to look at a system where particles interact through a so-called hard sphere interaction. Okay, hard spheres means that well, one way to think of it is that the potential is either 0 or it is infinity, and it is infinity when particles are closer than some distance. Well, in this case, in this Gross-Pitagoric regime, some distance of the order 1 over n, because we want the effective range to be 1 over n. Another way to write the hard sphere problem is that you don't write the potential energy, but when you restrict yourself, you take the minimum to get the ground state energy, you restrict to set to wave function which satisfy this condition. The wave function must vanish whenever there are I and j, I different than j, so that the distance between xi and xj is smaller than this a over n. Okay, so that's what it means to have this hard sphere. You want to exclude the possibility of these spheres to overlap, essentially. Okay, and then recently with Giulia Bastis, Serena Cenatiempo, Alessandro Giatti, and Giulio Pascoletti, we were able to deal also with the case of hard sphere. The formula is always the same. Okay, it's not at the end it is universal. It only depends on the scattering length, but the proof, the derivation of the formula is different in the previous case and in the case of hard spheres. So this is one extension of the result I discussed. Another extension concerns so-called trapped gases. So far what I talked about, we always assume particles to move in this box with periodic boundary condition. Okay? So instead of that, you could let your particle move in R3, but when you want to confine them, and you confine them with some external potential. Okay, that's also a natural question. In this case, the Hamilton operator describing the system has this form here. The kinetic energy is always the same. Now there is this external potential which confines the particle, so you assume that it goes to infinity as x goes to infinity, and the interaction is like before. And the difference is now this operator does not act on the box, it acts on L2 of a full space R3n. Okay? Good. Now, in this situation here, what was known from the work of Lieb, Saring, and Inverson is that to leading order, the ground state energy divided by n, the ground state energy is given by, to leading order, n times the minimum of this Gross-Pitagoric energy function. Okay? So if you are in the box, this kind is 0 on the box and it's infinity outside, so the minimum is when phi is equal to 1. And then you come back to this 4 pi a, right? But if you have an external potential, of course, this changes, and you have a nonlinear functional to minimize in order to find the leading order of the ground state energy. Good. And then Lieb and Salinger, of course, also proved condensation in this setting, so they prove that if you take the one particle radius density, now if you have an external potential, condensation will not be in the flat zero momentum wave function, it will be on a wave function phi gp, which minimizes this energy function. That's how you determine the ground state to leading order. Okay, so these were the corresponding of the sort of older result, and these are then the improvement, similar to the one in the translation invariant setting. So here it's a bit more difficult to read because you cannot characterize, you cannot label excitation with momentum, of course. Momentum is good if you are translation invariant, when you go to Fourier space. If it's not, then it's a little bit more uglier to write, at least. So here is the excitation spectrum. I didn't even write the formula for the ground state energy. You can compute it, it's not very nice. But for the excitation spectrum, again, you have integers ni times some energies ei. This is the energy of the excitation I, and this is the ith eigenvalue of this operator here on the one particle space. So maybe it's not so important what is the precise formula, just wanted to point out that it's possible to characterize the excitation spectrum also in this case. And in this case, we had, our work with Christian Benneck and Severin Schraven, and there was another work with slightly different techniques, more or less at the same time, of Nam and Arnaud Trier. Okay, so this is another extension. This is another related subject. So I'm discussing here results describing this Gross-Pitayevsky limit, where you have these n particles in the box, scattering length of the order 1 over n. Of course, there are other possible regimes which can be considered and which are certainly interesting. Maybe the best known from the statistical mechanics point of view is the thermodynamic limit. So in the thermodynamic limit, we still have n particles, but now the particles move in a box with volume L cube. And we let at the same time n and L go to infinity, keeping the density fixed. So the density rho divided by L cube is fixed. Okay? And then again, you can ask what is the ground state energy to different order. So now here you want to, since you want to let n go to infinity, you have to look at the energy per particle. So we divide the n by n, and we let, as I said, n and L go to infinity, keeping the density constant. And what was predicted by Li, Wan, and Yang already in 57 is that you should get this 4 pi a times the density, 1 plus this correction here, and then smaller order terms. Okay? So now, smaller order in the dilute limit as rho go to 0. Right? First you take the limit n go to infinity, L go to infinity with fixed rho, but then you're interested in what happens for small rho, and this is what you should see. And now one can rigorously prove this result, at least for a large class of potential. So upper bounds, yeah?
What do you mean smaller error?
Smaller means, you see, this is order rho to the 3 halves, and the next one is going to be rho to the 5 halves or something like that. You see, as the rho go to 0, in that sense. Yeah, first you take the thermodynamic limit, okay, and then you look at small rho. So after that you let rho go to 0 in a sense. Okay, so the upper bounds, there was a sort of a bit of older paper by Yao and In, which we managed with Serena and with Giulia to simplify and to extend, and we have a proof for the upper bound to this order. And the lower bound were proven by Søren Fournet and Jan-Philippe Solove, also in the last years, okay? At least to the second order. The one to the first order was already Liebing-Iverson in 98. Okay, that was the thermodynamic limit. Another related subject, I discussed so far the spectrum of this operator Hn. But as I said at the beginning, there is a relation between the spectrum and the dynamics, of course, because the dynamics is generated by the Hamilton operator, is the solution of this Schrödinger equation. Okay, so that's a natural question also, therefore, is to ask from the dynamical point of view what we can say. So these are kind of the results which one can prove. So here you start with, so the picture that we have in mind is the one of this first slide with these pictures, right? So what happens there, and what happens in general if you want to study the dynamics of a many-body system. So what happens is that you first impose some external field, and then you lower the temperature so that your system essentially relaxes to the ground state of the system with external field. But then nothing moves, of course, because you are at equilibrium. So what you do is you turn off the external field, so you're not at equilibrium anymore, and the system starts to evolve in this situation, okay? And then you want to say something about the evolution which results from turning off the external field, or if you want, from a change of external field. Okay, so it is natural to look for initial data which describe systems close to the ground state, at equilibrium, okay? And if you have a wave function which describes a system close to the ground state, well, we know then that this 1 minus this expectation should go to 0, because initially we have condensation, okay? And we proved that if you are in the ground state or close to the ground state, then this is going to go to 0. We even proved with rate 1 over n. Okay? Not only this should go to 0, the energy should be described to leading order by this nonlinear Gross-Pitayevsky energy function. Okay? And if you assume that an and bn go to 0 at time t equal to 0, so this is a characterization of the initial data that you want to consider. Then you can look at the time evolution, which is now generated by the Hamiltonian without external field. You see, the difference between this trapped Hamiltonian and this HN is that now I turned off the external field because otherwise it's not going to move, right? If you are in the ground state and you look at the dynamics, nothing interesting is going to happen. Okay, so then you look at the time evolution without external field, and what we prove is that at time t, you still have condensation with a rate which is again of the order 1 over n, if it was of the order 1 over n at time t equal to 0. So if these two, an and bn, behave as 1 over n. Of course, you have condensation in a new state, right? Because the condensate is going to evolve, and the new state is the solution of a time-dependent Gross-Pitagiersky equation. Okay, so you should think, on the one hand, you have the many-body dynamics, solution of this Schrödinger equation for n particles, and if you have condensation at time 0, then on the one particle level, most particles are in the state phi, how do they call it, phi gp, but then you start the evolution, and then you have the linear many-particle evolution translates into a one-particle non-linear evolution, which is described by this equation here. Okay, so this, I mentioned here the result that I got with Christian Bernecker, which is optimal in the sense of rate of convergence, but there were also results before. I started working on it with Laszlo Erdős and Don Seriao, and then also Peter Pickel had some results in this direction, and then another paper that I wrote with Niels Benedikter and Gustavo de Oliveira. Okay, so this is an approximation of the dynamics in terms of the reduced density. You can also ask about a norm approximation of the dynamics. So norm approximation, it means that I want to find an approximation for the solution of the Schrödinger equation, which I write here, in terms of something which is simpler and it should go to 0 in norm. Okay? So I told you at the beginning, right, the fact that gamma n converges to something does not mean that the state converges to something immediately. And in fact, here it is not enough to look at the solution of the Gross-Pitagiersky equation to get a norm approximation. You also have to describe the dynamics of the excitations. And now, without going into the details, but it is possible to find a quadratic dynamics, or a dynamics on some Fock space whose generator is quadratic, and maybe in a second it will be a little bit more clear what this means. Anyway, a simpler dynamics which allows us to approximate this many-body evolution. Okay, good. Maybe in the last, I don't know how many minutes now, 10, 15 minutes, I can try to say something about some of the vague ideas of the proof of the results that I presented. I mean, so these are all based on a rigorous version of Bogoliubov theory. So instead of explaining to you the rigorous version that we developed, let me first explain the heuristic version of Bogoliubov theory, which goes back to the work of Bogoliubov in the 40s already. In order to explain what Bogoliubov theory is, I need to switch to a new representation of the system on the so-called Fock space. The Fock space is what you obtain if you take direct sum of all these spaces. So the idea is you don't want to fix the number of particles, right? Earlier I was talking about system of capital N particles. Now I want to allow for the possibility of the number of particles to change. And therefore I take as Hilbert space, I take the direct sum of all possible number of particles small n. Good. If you are on this Fock space, it is very convenient to introduce this creations and annihilations operator, which allows you to jump from one subsystem to the next, either in one direction or in the other. And now you can do so for every momentum, and so we are still in this box, right? So momenta are discrete, and they are to be chosen in Z3, essentially. So for every momentum, you can define a creation operator A star P and an annihilations operator AP, which create or annihilate a particle with momentum P. Okay? Now, the formula, the precise formula, maybe not so important. What is a little bit more important is this operator satisfy canonical commutation relation, which I wrote here. A and A star of the same momentum give a commutator 1, everything else commutes nicely. Good. Now, an important observation is that if you multiply the creations operator and the annihilations operator, you take this product here. So this guy here, this operator, it measures the number of particles with momentum P. So the total number of particles of the system is the sum over all P of this A star PAP. Okay? Now, of course, you can ask, we're looking at a system where the number of particles cannot be changed by the Hamiltonian. The Hamiltonian commutes with the number of particles. So why do we care to take the direct sum over the possible? Why do we care for the possibility of changing the number of particles? And this, I hope, will be clear in the next slide, or in 2 slides maybe. First, let me rewrite the Hamilton operator. Okay, so this is the kinetic energy. So how do you compute the kinetic energy? Well, you count the number of particles with momentum P, you multiply with P squared, and you sum over possible P. And this guy here is just the potential energy. Now, potential energy was a 2-particle operator. It was V of xi minus xj. Since it is 2 particles, it's going to be quartic in creations and annihilations operator. And if you do the math and you go to Fourier space, you find this expression here. Now, this looks maybe fancy if you're not used to it. It is exactly the same Hamiltonian as we had in the previous, in the slide number 1, or in the previous slides in the different representation. So far, nothing changed from what we did before. So now comes the idea of Bogoliubov. So Bogoliubov knows that there is this Bose-Einstein condensation. Okay, Bose-Einstein condensation means most particles are in the state with momentum 0. Okay, so if you take A0 star times A0, that's the number of particles with momentum 0, it should be of order n. Okay, so both of them should be of the order square root of m, which is much larger than the commutator between them, because the commutator is always 1. Okay, so since you have this thing here, you are allowed, okay, and this is of course not a rigorous proof, but it's a heuristic argument, you're allowed to think of A0 and A0 star as commuting numbers. Right? Because the fact that they are operator and they don't exactly commute is, well, sort of irrelevant since the commutator is so small with respect to the number, with the size. Okay, so what Bogoliubov did, you take the Hamiltonian here, every time you see A0 or A0 star, you replace it with a factor of square root of n. Okay? And if you do that, then you find this Hamiltonian here. Okay? Well, right here I don't see A0 and A0 star, because I put P equal to 0 here, it multiplies with 0, so it goes away. But here I do see, okay? So the main term is the one where all indices are equal to 0. Then this guy is n squared, this is n, so you get this factor here, and then v hat of 0. So this creates this term here. And then you have terms where 2 of them are 0 and 2 of them are different from 0. You have terms where 3 are different than 0 and only 1 is 0, and you have a last term where all the indices are different from 0. Okay? Good. So now you start to see why it's useful to switch to this Fock space representation, because if I look at this Hamiltonian here, now there are terms like these two, this guy here and this guy here, which do not preserve the number of particles. So this guy creates 2 particles, this guy annihilates 2 particles. And why is it so? Well, because now we switch up our representation. We remove the condensate, right? And if you remove the condensate, the number of particles is not conserved anymore. You may have some interaction which move particles from the condensate to the non-condensate part and vice versa. Okay, so if you want to factor out the condensate, the number of particles is not conserved anymore, and that's why it's very useful to be on this Fock space representation, because this allows to describe this kind of processes. Okay, good. Now the next step of Bogoliubov is, well, you see there are these last 2 terms. They don't contain A0 anymore, so all the A and A star should be heuristically counted as order 1, but they still have a 1 over root n and 1 over n factor in front. So they should be small. Okay, as n goes to infinity, we can ignore these terms. That was his point. Okay, so then you ignore this guy, you ignore this guy, and you end up with a new Hamiltonian, which is now, I don't have the formula for the Hamiltonian, apparently. If you ignore these last 2 lines, you have a quadratic Hamiltonian in the end star. And if you have a quadratic Hamiltonian, you can diagonalize it. Okay, so it means the following. You can introduce what are now called as Bogoliubov transformation, which is unitary operator given by the exponential of a quadratic expression in A and the star, which generate rotation or symplectic rotation of A and A star. There are explicit formula here. And of course, if you choose this phase tau p in the right way, and you apply this t to the Hamilton or to the quadratic part of the Hamiltonian, right? I should go back 1 slide here. I apply T and T star, I conjugate with T, right? I forget about this part here. And when you conjugate this, each A star and A will rotate a little bit. But if you choose the coefficients correctly, you can make sure that the coefficient in front of the A star and the A parts vanish. And if you do that, you find something like that, where you have just a constant now and something proportional to A star P, AP. Okay, there is no A star, no AA left. So in this sense, the expression is now diagonal, and we can compute the spectrum, right? Because A star P, AP, the spectrum of this is the operator measuring the number of particles, the spectrum is just the natural numbers. So once you have this expression here, it is trivial to compute the spectrum of this operator. And if you do it, well, then you see what is the result. The result is this would be the ground state energy, and this would be the excitation spectrum. But it is not exactly what we had in our theorem. So this method does not lead to the right answer, and it does not, because instead of seeing the scattering length, I see everywhere this V hat of 0. And then Bogoliubov, however, knew, well, V hat of 0 is not a physically correct quantity. You have to replace V hat of 0, and also the second order expansion for the scattering length, by the scattering length. And if you do the replacement, right, just so ad hoc, then you find the right formula for the energy. Okay? But of course here, if you want to do this argument rigorous, you have to understand better why you should do this replacement here, because here I'm replacing, I don't know, 5 with 7. That means these are two different numbers. Okay? And of course, V hat of 0 is the first Born approximation for 8 pi of A, but this is not close in any sense. Okay? And the point is that doing this substitution here, you are making up for the errors which you made when you ignore the cubic and the quartic part. The cubic and the quartic part of the Hamiltonian, which you just cancelled because we said it was small. It is not small, in fact. It is the part which is responsible for renormalizing the potential and creating the scattering length and generating this formula for the limit for the energy. Okay, so that's the idea of Bogoliubov theory. Now, of course, we had to do it in a rigorous way, and so we developed a kind of a scheme, right? So the main issue, as I was trying to pointing out, right? You want to understand how these two parts here are going to renormalize the Hamiltonian in the first part before you do this quadratic approximation, and that's the whole point. So we developed techniques in order to extract from cubic and quartic term contributions to the energy which are still important, they cannot be neglected, and once you extracted it, so either as a constant or a quadratic term, you are going to change the operators in the first two lines, and at the end, once you know that these are small, you can indeed prove the formula that I had in the theorems. Okay, thank you very much for your attention.